Thanks everyone for joining me here in this session on designing for modularity with Java modules. As said, my name is Sander Mak. I come from the Netherlands and I work with a company called Luminous. And we are a software technology company in the Netherlands. And we do consulting work, we do project work, but we also build our own products. And as many of you may know, building products is a different story, right? If you're going to create a code base that you have to support for 5, 10, many years with a large team and everything that comes with that, then you really need to start thinking about how to keep this code base maintainable, extensible, not just in the short term, as you would do with consultancy and small projects, but also in the long term. And we truly believe that modularity is one of the key principles, one of the key mechanisms to create such extensible, maintainable, and flexible code bases. So I've had some extensive experience already creating modular code bases using, for example, OSGI. And of course, when Java 9 was announced and it was actually known that Jigsaw was going to end up in Java 9, this caught our attention. And me and my coworker, currently former coworker, Paul Bakker, we actually decided to jump on that and to get some real experience with the early access builds already in 2015. And one thing led to another, and this also led to the book that you see here, the Java 9 modularity book. And essentially what we did is we tried to transfer our knowledge of what we learned of modular development, for example, using OSGI, into this new world of Java modules. So in this talk, I want to share with you some principles and some patterns that we learned, that we also described in the book, that can really help you to create extensible and maintainable code bases. So this will not be an introductory Java modules talk. I will not really dive into all the basics of the module system, though we will get a module primer in the beginning. It will be very quick. We'll review the basic concepts in just like 5 minutes. And after that, we look beyond that. And we're going to look beyond that because that's what you need to do if you want to build real applications using Java modules or whatever module system you choose. It's about the architectural principles and how they map to the technology that you want to use. So after we've had this module primer, we're going to look at another layer that lives on top of modules in the Java module system, which is the services layer. And we'll see that services are an essential concept to actually decouple modules. But we generally work with applications that also use different forms of inversion of control, like dependency injection, using Spring or whatever framework you use. So we're also going to look at how these two worlds come together. What about using both modules and a dependency injection framework? And we'll see that it's not that trivial yet to do so. After looking at services and dependency injection concretely, we're also going to look at some more abstract design patterns if we're going to design modular applications and how they map to the constructs that we get in the Java module system. After that, we're going to look at a more advanced topic in the sense that it is aimed at being able to load code at runtime. So dynamically load new functionality into your application, like in a plugin-based system. And this is not something that is for all applications, but if you need it, it's really useful to know how to do so using the Java module system. So that will be our final topic. So in this talk, we're not going to focus on migration paths. So we're not going to take your existing code base and see how we can modularize that. If you want that, there was a talk about that yesterday by Rabea Gransberger. I urge you to look at that, and you will get a good overview of how to actually migrate existing code bases. But for this talk, let's just forget about the existing situation with the messy class path and these big messy monoliths that we built on top of them. What about if we embrace modules fully? We go all in modules. What would that mean? And how would you use a module system to create truly modular software? So this is all about the design of software. It is also about constraints, because modularization means you constrain yourself in some ways to actually get the benefits of maintainability and extensibility. So we'll look at some of the constraints that are imposed by the module system upon us, why they are there, and how you can handle them. And of course, this leads to some patterns that we'll see, and I've already said, for example, using services is one of those patterns that can help you make the most of the module system. Now, as promised, a very quick module primer. So to create a module, you actually have to create a module descriptor, which lives in module.info.java. And you see two examples here of a module descriptor. There's one called EasyText CLI and one called EasyText Analysis. You'll see EasyText coming back more and more in this presentation because it's the sample application that we created for the book and that I also used to explain all the concepts that we're going to talk about today. And on the EasyText CLI module descriptor, we see that it has a require statement. And this is an explicit dependency from the EasyText CLI module to the EasyText Analysis module. And it means that the EasyText CLI module can now make use of code that lives inside of the EasyText Analysis module. So far, so good, pretty simple, right? And this information can be used by both the Java compiler, the Java runtime, and any other tools that understand the module info descriptor to actually verify and help us enforcing these dependencies. Now, if we require another module, it doesn't mean that we can see all code that's inside of this module. No, we need to explicitly export packages for them to be usable outside of the module and to be usable by other modules that require, for example, EasyText Analysis. And exporting is something that you need to do deliberately. If you don't put an export statement for a package in your module descriptor, it will be encapsulated by default. And encapsulated means it's just internal implementation details for your module. So no other module will be able to reach it, not even through reflection or any other hacks. It will be truly encapsulated. And this is a mechanism that is used inside of the JDK, for example, a lot to encapsulate these internal implementation packages and classes of the JDK, so they won't be abused anymore as they have been in the past decades of Java. So the exported packages, they sort of form the API of a module, if you want to think about it in that way. That means that you need to be very deliberate about what you are going to export to the outside world, because whatever you export, you must support and you must evolve, hopefully in a backward compatible manner. So this is something that you shouldn't do lightly. In essence, you want to keep as much as possible of the implementation of a module internally, so you can change it without affecting consumers. So you can maybe even swap out parts and just rewrite parts without affecting any of the users of the module. Now, there's also a opens keyword here, and we'll get back to that later. But in essence, we have many frameworks in Java that do use reflection at runtime to do their work. Think of, for example, Hibernate or Spring. Spring tries to instantiate your service classes, so it needs to reflectively access your classes. It needs to maybe inject into private fields, so it also needs to do so-called deep reflection, so not just reflecting on public parts of classes, but also breaking into private parts of classes. And this sort of has a tension with modularity, right? Because encapsulation that we talked about is in essence violated if we allow these frameworks to pry into private details. But at the same time, they're very useful frameworks and we want to use them. So opens is a middle ground between full encapsulation, which is the default for packages inside of modules, and exporting, which means you publish something as public API and people can compile against it and can actually depend on it. An open package is in between in that at compile time, you still cannot access anything that's in the impl package in this case. So you cannot, as a developer, code against any types that are in the impl package statically at compile time. But at runtime, things are a bit more lenient. And the JVM will allow other modules to gain access to types inside of the impl package. For example, to instantiate them reflectively. And also, it will allow deep reflection, so opening up of private parts of these types using an open package. And we'll see how that will be useful when looking at dependency injection in Java. Now, any other packages that might be in a module that are not opened or not exported are fully encapsulated. So these are really, really internal to the module. So the takeaway here is we have requires, and requires takes a module name. So you have a dependency graph of modules expressed using the requires statements. And we have, on the other side, exports and opens statements that govern what is visible and what is usable outside of the module by other modules. Now, onto services. Like I said, I assume most of you have heard or seen the stuff I talked about earlier. So let's look at some usage patterns of modules. Because you'll quickly find out that if you only have the requires, exports, and opens statements at your disposal, you will run into some pretty interesting issues if you want to create truly decoupled modules. So the example that we're going to look at is a simple application with two so-called front-end modules, the EasyText GUI and the EasyText CLI module. And the EasyText CLI module is just a command line interface which reads in a file containing some text, and it can calculate a complexity metric. And the GUI does the same, only you can paste or type your code into the GUI. Now, the idea is that ultimately we want to have multiple of these complexity metrics available. For example, in the GUI, you can just select one in a dropdown. And of course, we can build this, and we can separate the analysis logic into modules, like you see on the bottom here, the EasyText Analysis Kincaid and EasyText Analysis Coleman. These are two complexity metrics that are living in their own modules. But if we need to be able to access code and to access these implementations inside of these two Kincaid and Coleman modules, then we actually need a require statement from the EasyText GUI and the EasyText CLI to these two implementation modules. And what happens if we, for example, want to add a third complexity metric? Then we would create a new module, but we would also need to change the module descriptors of EasyText GUI and EasyText CLI to add this new dependency. We need to change the code to find out about the new implementation class, instantiate it, etc., etc. And at the same time, the implementation modules of the complexity metrics need to expose their implementation classes. They need to export these packages for them to be usable by the two front-end modules. So while we do separate the logical parts of our application into modules, there's still a very tight coupling going on between those modules that we actually don't want. So what we really want is that we want to have some API, so some analyzer interface in between, which, for example, lives in the analysis API module. And we want our EasyText GUI and EasyText CLI modules to only know about this API, to only know about this analyzer interface. And somehow it should be able to get a hold of implementations of this interface without explicitly knowing where they come from. Now, this sort of sounds like inversion of control, right? This is the original problem that also dependency injection frameworks try to solve. And indeed, this is also solvable using services in the module system. How are we going to do this? Because even if we have this sort of analyzer interface, we still need to get a hold of the implementation. And we could instantiate an implementation class, like doing new Kincaid analyzer, but it means that it would have to be exported from the implementation module, and it would sort of avoid our issues that we talked about earlier. This is really a solution. And it will need to be exported from the Kincaid module, like I said. This is still the old situation. Some people think, okay, well, maybe we can just forget about the require statement and somehow use reflection to find the class and instantiate it. And yes, you could do that. But as we learned before, then the package in this implementation module still needs to be open. And what will happen at runtime is that when using class for name, a readability relation or a requires relation will be established automatically because of the use of reflection. But at the same time, you still need to know the name of the class to instantiate it this way. And it still needs to be in an open package, which is, okay, it's better than being in an exported package, but it's still not really a solution. So fortunately, there's a real solution to this. And like all problems in computer science, we just solve it by adding another layer of indirection. And in this case, the new layer of indirection is a so-called service registry that lives with the JDK in the module system. And what we can do is we can instruct the EasyText Analysis Kincaid and Coleman modules to become so-called provider modules that register an implementation in the service registry. And we can have the EasyText GUI and the EasyText CLI modules be so-called consumer modules that request instances of the analyzer type from the service registry. So this picture we still see how there's collaboration between these modules without having a direct requires relation between them. And it looks like this in code. So from the provider side of things, from the implementation side of things, we can create a module EasyText analysis Kincaid with this module descriptor, where we still require our API module because, well, we need to know about this analyzer interface and we need to implement it. But instead of exporting a implementation class like we did before, we're going to use a new construct that's also available in module descriptors. And here it says, okay, this module provides something of type analyzer, which is the API analyzer interface, and we provide it with Java Modularity EasyText analysis Kincaid analyzer. So this is our implementation class. And as you can see, there's no export statement anymore for the Kincaid package, which is exactly what we want. So the services mechanism is powerful enough to be able to reach into our module, even though it's not opened or exported, and reach into this implementation package, instantiate it for us, and provide it to any consumers. So the implementation of such a service in a provider is just a plain Java class. There are no special APIs to use or special APIs to implement. We just have the Kincaid analyzer that implements the analyzer interface. We have some analyze method, and the only thing that's different that's added here is a default no-arc constructor that's used by the services mechanism to instantiate it. If you don't like this default no-arc constructor, you can also provide a static provider method that returns an instance. So you can do some magic there to do singletons or to do caching or to whatever you want. But this is the easiest way to expose a service. Now on the consuming side of things, things look slightly different. We have our CLI module, for example, which was one of the two front-end modules. And this one requires, again, the API, because it also needs to know about the analyzer interface, because it wants to call methods, most notably the analyze method. And then, instead of requiring the implementation modules, we can just say to the module system, okay, we use we use instances of the analyzer interface. And the module system will be able to provide these to us. Now, inside of code, we still need to get a hold of these instances, and we do that using the service loader API. The service loader API is actually a pretty old API. It has been in Java since Java 6, and it has been used by some frameworks and also inside of the JDK itself. But before Java modules came along, you had to use the service loader by creating sort of text files in the meta-inf services directory containing the mapping from the interface type to the implementation type, and it was sort of, it wasn't really easy to use. So modules changed that. We can now easily use services from within the module descriptor and create decoupled modules this way. So if we call service loader.load for our given type, in this case the analyzer interface, analyzer class literal that we pass here, then we will get back a service loader object. And the service loader object conveniently implements iterable, so we just assign it to iterable here. And then we can do a for each loop over this iterable and get back all the instances that the service loader was able to find and instantiate for us. So this is a runtime coupling that comes about by using the service loader mechanism. And you might find one implementation of analyzer, you might find multiple, you might find zero. So this is something that you should code for in your application, that you should take care of yourself. But it really allows us to create a consumer module that doesn't have a hard compile time dependency anymore on the implementation modules, on the provider modules. So this is exactly what we were after. And this solves the problems that we talked about in our first picture that we looked at. Now, what we just did was ask the service loader to give us all instances it could instantiate. You can also use it in a bit different way, and in that case, we're going to call, again, service loader load. But now we're going to treat it as a service loader object, and then we call stream on this service loader. And stream will give us back a stream not of the actual instances of the services, but of so-called service loader.provider instances, which describe the instances that are available. And this service loader provider descriptor allows you to get back, for example, the concrete class type of the implementation. So you could, for example, filter it and check if there are any annotations on this class. Maybe you use annotations to distinguish between different implementations, and you can find the one that you're interested in. And afterwards, here in the map method, on the providers that you actually want, you call get, and then it will instantiate it for you, and you will get back the analyzers in this case. So this is one way to do lazy instantiation and also filtering of services on the consuming side. So what this allows us to do is to create an application that is extensible in a sense that we don't have to recompile our application, we just have to add modules that provide implementations of the service, and our application will grow in functionality. And I want to show this in action in a small demo that I have. So what we see here is the EasyText application broken up into multiple modules. And just to show that it's the same code as we discussed earlier, there's a simple Java interface containing getName and an analyze method that gives back the metric that we're interested in. And there are two provider modules in this case. So let's open up, for example, the Coleman provider module. Again, it's a simple plain Java class that implements the analyzer interface. It gives back the name so we can render it in our user interface. And it implements the analyze method. So here's the implementation of the Coleman metric. And most importantly, of course, in the module descriptor, we have this provide statement where we indicate to the module system, to the service registry, that we provide an implementation of Coleman analyzer, with the Coleman analyzer class. And again, note that this package, where the implementation lives, is not exported, is not opened in any way. So we can refactor this, we can rename this, we can do whatever we want without impacting any of our consumers. So this is actually what you're after if you want to create really decoupled modules in your application, if you want to create an extensible application. Now, on the consuming side, it shouldn't surprise you that you have a user statement. And again, we use the analyzer type here. And just to show how it works from the code perspective, our main class contains the service loader.load call, and it just iterates over all the analyzers that it finds, and it calls the analyze method to print out the resulting metrics. So just to prove that it's not just some pretty code, but it's also working, I can run this on the latest Java 10. And as you can see, we get a drop-down containing our two implementations. And I can just call them and get back the metric. And most interestingly, let me close this, is that if we look at our modules directory, and the jars that I'm running are in here, and I, for example, just throw away one of the provider modules, so there goes the Coleman jar, and I'm going to just run the application, so I'm not going to recompile, I'm not even creating new jars or anything. I'm just going to invoke the Java command with the module path pointing to our jars and our libraries that we use, starting the EasyText GUI module again. Then you will see that we only have a single algorithm left. And this also works the other way around, right? I can just add modules that provide services, and they will become available without any recompilation or without any other code changes. Now, of course, one of the questions is, it's nice, but you have to restart the application. Can you also do this dynamically? And that's what we're going to look at towards the end of this session. So that was services. But I can hear most people thinking, well, that's nice, but it's sort of a service locator pattern, and it looks sort of old-fashioned, right? We have to do this load call, and then we get the instances. Please give me back my add inject. All right, let's try and do that. So we're going to look at how modules and dependency injection actually interact. So our goal here is to take the same application and to get the same functionality, only now, instead of using the service loader, we want to use our add inject annotation so that the Kincaid and Coleman implementation get injected into our front-end modules, in this case the CLI module. Now, I want to show this example using Juice, but the general patterns can be applied to any dependency injection framework. So what you need to do in Juice is you need to configure your dependency injection framework. And this configuration is provided in so-called abstract modules from Juice. And this may get a bit confusing because we now have Java modules and we have Juice modules. But what you see here is such a definition of a Juice module. And in the configure method, we actually instruct the framework that, in this case, if it needs something of type analyzer, it should consider this common analyzer class. So in fact, this is the same metadata that we just expressed in our module descriptor, only now we express it to our dependency injection framework. And you might do the same thing in Spring Java configuration or even in Spring XML configuration. It's all the same idea. We somehow need to instruct our dependency injection framework to know where the actual service instance is and what type it conforms to. So that's what's happening here. Now, the consumers, they somehow need to get access to this Juice module configuration because they need to use that to instantiate the application and to bootstrap the bootstrap the Juice dependency injection framework. That means also at the same time that the implementation package containing the implementation of the service needs to be open, because where the services mechanism had this sort of special power to reach into our encapsulated package to instantiate the service, Juice or any other Spring framework or any other dependency injection framework is just a regular piece of code which doesn't have these magical powers. So for reflection and reflective instantiation to work, the implementation package needs to be open. So what we end up with in this case is a Java module containing our Coleman Analyzer implementation class, but also containing an additional package called Juice, which contains the Juice configuration module that we call Coleman module here. And of course, we still have our module info.java containing the module descriptor. And it looks like this. So let's focus on the lower part first. We need to export the Juice package here, because we somehow need to bootstrap our whole application later on, and we're going to use the Coleman module configuration as part of this bootstrapping process to get the dependency injection going. At the same time, I already spoke about this. We also need to open the actual implementation Coleman package containing our Coleman Analyzer class, because it needs to be instantiated reflectively by Juice at a later time. So opens is only at runtime, right? We still do not expose our Coleman Analyzer class to developers at compile time. Now on the top we see that we still require EasyText algorithm API, which makes sense because it contains the analyzer interface, but we now also require Juice and the Juice multi-bindings module. And multi-bindings is just so that you can bind multiple implementations for a single given type. But does this mean that Juice and Juice multi-bindings are actual Java modules? No, that's not the case. These are so-called automatic modules. And if you want to know more about that, again, watch Rabea's talk from yesterday online. And she explains everything about them. But the very short version is, if you have a jar file that doesn't contain a module descriptor, and it's currently running on the class path, then you can just pick it up and put it on the module path, and it will behave as if it were a module. And it will just export all of its packages, and it will get a dependency on all of the other modules, so it will be a very bad module, but still you can use it and you can refer to it as we do here. So we don't have to wait for Juice to actually get module descriptors and to be, to get modularized itself, which is nice. So what we can do now on the CLI side of things in our main method is to create a so-called injector, which is comparable to application context in Spring. And this injector uses the Coleman module configuration and the Kincaid module configuration to actually find out what's going on. And we can finally instantiate our CLI class, or actually get Juice to instantiate it for us. And in the CLI class, it will now inject for us the analyzer implementations. We can now finally use this add inject on the CLI constructor, for example. And it will get all of the implementations. So this wasn't easy, right? This is really some multi-step thinking and some real insight that you need into how modules work and to how Juice works. So this is something that will still need some more evolution, in my opinion. So Spring Framework, Juice, etc. It's usable already, but it really requires some thought. So what happens here actually is that we create this binding in our common module using the Juice APIs. And then, of course, our CLI module now requires this Juice module configuration of the common module. And this allows it to create an injector that actually knows how to inject back the instance of the common analyzer into our CLI. And like I said, this is really ideal. And if we look a bit further, then we also see that we also still need to require the common and concate implementation modules for this to work from the front-end modules. So this actually doesn't really solve the issues that we could solve using services. Now, this does mean that we get some benefits, right? We can use the add inject notation again instead of using the service loader API. And you might be more familiar with this model, but it does still give us some downsides because we still need to require the implementation modules. We need to update our module descriptor on the front-end modules if we actually add new implementations, which is something that we didn't have to with services. And another thing is that the services, as you use them in the module descriptor, are actually checked by the compiler. So if you use any types that don't exist or things like that, you will get warnings. Again, this is something that is less obvious when using dependency injection framework. Now we can improve on this situation by combining services, and in this case, Juice, to get the actual decoupling that we needed and that we had in the services situation. So this is where we ended up when doing dependency injection with Juice in Java modules. So what we want to get rid of is this export statement where we exported the common module configuration. And what we can do is instead publish this as a service to the outside world. So we say, okay, we provide this abstract module type, that's a Juice type, and we expose it as a service, and it uses the common module that we saw earlier. And then we don't have to export this anymore. And this also means that the require statements that we had in our front-end modules, which were only there to get the common and the concate module dependency injection configuration, we can leave those out and we can replace them by a uses abstract module statement. And this way, we can change our bootstrapping code, in this case of the CLI module, to instead of directly referring to this common module and concate module, to actually call service loader load and say, okay, give me everything that implements this abstract module type of Juice, and use that to create the injector. And this way, we now finally have the decoupling that we want, and we can still use the injection that in this case Juice offers. So that was dependency injection and services. But there's more to think about when you think about modular design of applications. So one thing that might be a bit surprising that I talk about first, but it's really important, is about naming modules. And like we know, naming stuff in code is just hard, right? And all too often we just give up and use some meaningless name. If you do that for modules, you failed. So what you instead should do is you should at least differentiate between application modules and library modules. So for application modules, what you should strive for is to excuse me. What you should strive for is to have really short and memorable names. So a nice convention would be to have your application name dot component name, and that might even be nested one level further if you have many subcomponents that again have subcomponents, etc. But try to keep it short and sweet. And the EasyText of GUI is one of example of this approach. On the other hand, if you are a library author or library maintainer and you want to publish your module, then uniqueness of the module name is actually very important because you live in a global namespace again. Like packages, modules must be globally unique in that sense if you create libraries. So a tried and true pattern there is to use the reverse DNS notation, and this is also recommended for libraries. So you will get something like com.mycompany.rlimp, and this this name of the module is typically what we call the root module, the root package of this module. So this is the longest shared prefix of all packages that are in your module. And if you already have Maven coordinates, for example, it might very well be that your Maven coordinates actually make for a really nice module name by just appending them and having the artifact ID at the end. So that's something that you should really think about first when creating modules. Now, there are different types of modules, as we already saw in the example of the EasyText application. So we, for example, had this analyzer API module. And this API module is something that only exports code. It doesn't have any internal implementation code. The question is, okay, when should I separate my implementation and my API? And the most obvious answer here is, okay, if you expect to have multiple implementations of an API, like was the case for our analyzer example, because we had multiple analyzer implementations that were independent, then it makes sense to create a self-contained and simple API module. Now, it's also perfectly fine to have a module that combines an API and implementation. So where you export just the API parts of your module, and you have an internal implementation, which you, for example, can publish using a service. And in that way, you sort of provide a single default implementation of the API. It doesn't mean that you can't have any additional implementations, because another module could just require your combined API and implementation and just provide its own implementation of the API. But you at least know that you always have an implementation available if you use this pattern. So inside an API module, we have obviously mainly Java interfaces. But a Java interface also refers to other types, right? It has parameter types, return types, exceptions. There might be enums, etc. These are the sorts of things that you should think about when designing API packages. And in a sense, this is really a design question that you should address upfront before creating a module. Now, another question that often comes up when you start designing modular applications and you start designing modular libraries is the question of, should I create many small modules or a bigger one or a really big one? Because on the one hand, if you have many small modules, this makes your application or your library more composable, right? You can just mix and match or pick pieces of whatever you want, and you can reuse them in different contexts. So that sounds good. On the other hand, if you have many modules, then it also becomes a bit less clear what you should use. And it really depends on the situation whether you should go for a really big or a small module. So can we somehow combine these things? And the answer is yes. There's a mechanism that you can use in the Java module system that allows you to create so-called aggregator modules. And what happens here is that, for example, if you have a library that logically consists of 3 parts, like mylib 1, 2, 3, you can create a new module which doesn't have to contain any code. It only has to contain this module descriptor. And you say, okay, this module requires transitive all the parts of my library. And what you can do now is with this sort of aggregator module on top, so mylib, which has the requires transitive to the 3 parts, is if you have an application and the application requires mylib, then because of this requires transitive statement, and this feature is also called implied readability, the application will get implied readability to all 3 parts that are in the mylib module descriptor. So this way, your consumer of your library only has to know about, okay, I should say just requires mylib, and under the hood, it will get access to all 3 parts. Or maybe even 4 or 5 parts if you have a newer version of your library with more modules. That's totally up to you, and as long as you update the mylib module descriptor, this aggregator module, then your consumer really doesn't have to find out. At the same time, you can also use this pattern in a similar but slightly different way, where you say, okay, I'm not going to create a single empty aggregator module, but I can chop up my application or my library into some core functionality and into some extra functionality which builds on top of this core. So what you would get in this case, that if the extra functionality requires transitive the core functionality, if an application now requires the MyLab extra stuff, then it will also get the readability to MyLab core for free because of the requires transitive. At the same time, it also allows the application to be more precise and to express the fact that it only depends on MyLab core if the application developer wants to do this. And this way, it will reduce the module graph that is resolved for the application. And in a modular world, it pays to be precise about your dependencies. So if you actually only use parts from MyLab core, then it pays off to be precise about this dependency as a developer and to say, okay, I only use MyLab core, because now, if you use tools like, for example, JLink to create small custom runtime images for your application, then it will not resolve MyLab extra. And it will reduce your module graph and make your application smaller. Another thing that the Java module system disallows is cyclic dependencies. And we all know, sort of from our gut, that cyclic dependencies are bad, right? And we should avoid them. And that's mainly because they make building code hard, they make reasoning about code hard, they make maintaining code hard. So cyclic dependencies is something that we should avoid, and we absolutely cannot have in the module system, because modules cannot have a cyclic dependency. So what happens if you do have code, like here, that does have a cyclic dependency, and you want to create modules? Then we somehow need to break the cycle. And in this example, we have a authors module and a books module, and there's an author and there's a book, and the author has a name and a list of books, pretty simple data class, and the book has, again, a reference to author, and well, this is, of course, what causes our cyclic dependency, right? So we have book referencing author and author referencing a list of books. Now, breaking the cycle is not something that can be done automatically for you. This is really about design of your code. And again, you need to think about this yourself. Well, in this case, if we reason about why the cyclic dependency exists, we can see that in the print book method, we're actually using this author to get the name to print it. And this is the only thing that we do from the book perspective with an author. Now, this might point us to a new abstraction. For example, something like a named interface, something that has a name, something that has a getName method. And it doesn't really matter whether it's an author or a computer-generated book later on, which has a different way of getting the name. We were not really interested in that. So we were sort of pointed towards a design flaw by the fact that we want to break the cycle. And now we can let this author class implement the named interface, and there's still the same getName method that just returns the name of the author in this case. And there's the named interface, just defining the simple getName method, which now lives in the books module, but we could also create a separate API module, of course, containing the named interface if we expect there to be multiple implementations. And a nice side effect is that in this case, author doesn't even need to be exported anymore, because we don't compile against it anymore from the book side of things. So again, breaking cycles is not strictly related to modules, but we're forced to break cycles anyway because the Java module system disallows cyclic dependencies between modules. You can still have cyclic dependencies between classes within a module or between packages within a module if you're so inclined. Of course, it's debatable whether you should want to do this, but you can. But if your cyclic dependencies span different modules, then you need to break the cycle. And that's not just for simple one-on-one cycles, but it's also if the cycle involves many, many modules. You will get an error from the module system. Then we should also talk about optional dependencies, because we saw everything so far has the requires dependency, which means that the dependency always needs to be there, and the application won't start or it won't compile if the other module that you require isn't there. But sometimes, and especially in frameworks, we also have optional dependencies, where in the class path situation, you might put a jar on the class path and it will get used, but if it isn't there, then it's fine too, then the framework will just ignore it or have some fallback implementation and run without this just jar. So how do we translate this pattern into the modular world? Now what we could do is use a so-called compile time only dependency. And it looks like this. There's a static modifier for the requires keyword, and the requires static means that at compile time, in this case, fast JSON-lib must always be there, but at runtime, it can be left out. It can be left out of the module path, and the application will still start. But what does it mean if we start the application without this module being present? Somehow, we need to code defensively, right? So the only way to do this is to use, again, reflection to instantiate, for example, the fast JSON type from this fast JSON-lib library. And if it works, it works. And if it doesn't, we get this reflective operation exception, and we somehow need to do our fallback scenario. So this is an okay solution, and it's sort of the mirror of what happens currently in frameworks that use optional dependencies. But I mean, this isn't really nice code to write, is it? So a better solution to the whole optional dependency issue is to use services. And what you can do now is, for example, as a framework, define some API, in this case a JSON API, and then indicate to the module system that you use anything that implements this API, in this case the JSON API. And as a framework, you can now call serviceloader.load and give me anything that implements this JSON interface. And here we're again using the stream and filter pattern to inspect the instance, the provider descriptors that we get back, and we filter it using the isFast method, and the isFast method just looks for some annotation or some other property that we know that marks the fast implementation, and then we try to find it. And if it's not there, well, then we use our own implementation maybe, or just skip using this dependency altogether. And this, of course, requires more control than just putting something on the class path or not, because you need to know that the optional dependencies that you're using is actually published as a service and conforms to some interface. But if you have this kind of control, this is the preferred solution. So this brings us to our last topic. And as I promised, we're going to look at how you can actually load code dynamically at runtime using the module system. Now, so far, our application just runs from the module path, and the module path contains all of our application modules. It will boot up. If something's missing, the module system will complain, so that's very nice. But if everything's there, the application will start, and these are the modules that are used. Now, under the hood, a layer is created for this module path. And if we run an application from the module path, only a single layer is created called the boot layer. And that's where all our application modules live, and also the JDK modules themselves live. So this is the picture that gets created at runtime. But a layer in the module system is immutable. And it contains your application modules, and it contains the platform modules from JDK. It can also only contain a single version of a module at the same time. So this sort of seems to imply that dynamic loading is not possible, right? Because you cannot add anything to an immutable layer. But fortunately, there's a solution for this as well, because you also have a so-called ModuleLayer API that allows you as a developer to create new layers at runtime yourself. And these layers, they form a hierarchy. So what you could do is start your application with fewer modules on the module path. So in this case, we only have our API module and the GUI frontend module, but not any of the analysis implementation modules. And then at runtime, you might create a new layer that contains new modules that you load at runtime. So here we have this Coleman module that we load into a new layer at runtime. And every layer needs to point to a parent layer. So this layer 1 points to the boot layer as the parent. And this parent relationship means that any dependencies of the Coleman module may be resolved within layer 1. But if something is not there in layer 1, then it will just try to find it in the boot layer. So there's delegation going on of module resolution. So in this case, we know that Coleman needs our API module. So it will resolve against the API module that lives in the boot layer. Now we can do the same for our Kincaid implementation as well. And this one is interesting because it's not a single module, but it's actually a set of modules that need to live together to implement this Kincaid analysis. And we see there that we, again, in the new layer, we load only the additional modules that we need for the service implementation, and it also resolves against the boot layer. So this is the mechanism that you can use to add functionality at runtime. And the nice thing is that you can also load different versions of the same module in different layers. So this is something that you can also use to work around restrictions of not being able to run multiple versions of the same module in a single boot layer. So our goal here is to take the EasyText application and to change it into something that's extensible at runtime, and not just by stopping and starting the application and changing the module path. So let's see how that works. And for that, I'm going to switch to the dynamic loading branch of this repository. Here we go. And I'm going to run the application again, just to show you how it works now. There we go. And as you can see, the drop-down here is now empty, right? There are no implementations of any algorithms available. So what I've added is a new button, Add Analysis, and we're going to add, for example, this Coleman analysis directory, containing, in this case, a single provider module, because everything's in there that does need to run the Coleman analysis. And if we add this, then suddenly we see that our application has been extended with this new Coleman analyzer functionality, and it works the same as previously. And we can do the same for the Kincaid analysis, but like I said earlier, this one is a bit more involved. It's not a single module, but it's actually a couple of modules that are related together. But we open this directory, we add it to the application. It creates a new layer containing these modules, and it adds these. And as you will see here, we now also have the Flash Kincaid algorithm again available. So this is just to show you that it works. Now, of course, we're interested in how this works. So if I go to our EasyText GUI implementation, then the module descriptor is still the same. We still have just the users and provides statements. But what is different is that in this case, we do an initial service loader.load call, but again, this returns 0 implementations, because on the module path there are no provider modules at startup. What happens is that if we click this Add Analysis button, is that we get a dialog asking us for a directory, and after we get back to the directory, we call this Load Analysis in Layer method, and it gives us back a new module layer, and this is the module layer that I talked about in the explanation earlier. Now, with this new module layer in hand, we can call the service loader again, now passing in this new layer, and we're still requesting the analyzer interface here, and then we get back all the new implementations from the new layer, and we can add them to the UI, update the UI, and everything's okay again. So of course, the most interesting stuff is in this load analysis in layer method, where we create a new layer. So let's move on to that. And as you can see here, we pass in the directory that we're trying to open. And this is a multi-step process if you want to create a new module layer. So what you first need to do is to create a module finder. And module finder is all about mapping to a physical location of the modules, in this case on our file system. So there's a convenience method, module finder of, that we just pass our path, and it will create a module finder for the given directory. Now, as I said earlier, every module layer points to a parent. In this case, our parent is the boot layer, which you can get by calling ModuleLayer.boot, the static method boot. And now we can create a configuration. And the configuration is actually what does the resolving of the modules, the logical resolving. So on this parent, we call the configuration, and we resolve and bind a new configuration by passing in our module finder. I won't discuss this in further detail, but if you want to know about this, look at the Java doc. But what happens is that we now resolve a new layer, a new configuration containing the modules that are found in the directory that we passed in. Now, the last thing that needs to happen is that we need to instantiate this resolved configuration into an actual module layer. And for that, we use the define modules with one loader class. and we pass in our configuration that we created, but we also need to pass in a class loader. And what happens is that with this method, a new class loader gets created that delegates to, in this case, the system class loader. And this new class loader is used to load all classes from the modules that are in our configuration. So in this case, the Coleman module will be loaded in a new class loader that's delegating to the system class loader. So this call, this define modules with one loader call. There's also a define modules with multiple loader calls, where a new class loader is generated for each module that's loaded into the layer. Again, it depends on your application, what you want to do here. And this finally gives us back the module layer that we need to pass into the service loader call. So this is a fairly advanced API in terms of the module system, and many applications won't have to use this, but if you do create a pluggable and extensible application that also needs to be able to add new functionality at runtime, by loading plugins at runtime, for example, then this is the API to look at and to use. So that brings us to the end of this session. And of course, I would like to point out again, if you want to know more about this, you're welcome to go to javamodularity.com. Contains information about the book. Also contains a link to GitHub, where you can look at all the code that we just saw. Also, I do have some courses on Pluralsight, and if you don't have a subscription, I can offer you a free month of Pluralsight. If you come up here, I have a course for you. Highly recommended. Some courses on Java 9 and Java 10 on there. And with that, I think there's time for 1 or 2 questions. So let's do that.
1 questions, please. Поднимаем руку, встаем, представляемся и задаем вопрос.
Thank you for your presentation. My name is Farid. What do you think about OCGI and Java 9 modularity? Can we combine this?
So the question is, how can we combine OCGI and Java 9
yes.
or Java 10? Yeah.
And
so yes, you can still run OCGI, and you would just run it on the class path of Java 9 or Java 10, and that will work. And in that case, you won't use Java modules, you will just use OCGI bundles. If you're asking about interoperability between OCGI bundles and Java modules, that is something that is currently sort of work in progress for the OCGI Alliance. So I think they're working on being able to express dependencies, at least on JDK modules, so that you can express from an OCGI bundle that you only have a dependency, for example, on the Java logging module or the Java base module or anything like that. But that's really something that's still in progress, so I can't really comment on how practically usable that is at the moment.
Thank you very much. And 1 more question?
There's 1 more, yeah.
The last question here.
Good day, thank you for your speech. It was really fascinating. My name is Sergey, and my question is continuation of the previous guy's question. What about necessity of SGI in the world of Java 9? Because I visited a lot of the speeches about Jigsaw, and I used SGI a lot. And still haven't got the clear answer on this question.
Yeah. So what is the relevance of OCGI when with Java 9 modules? And I think there's 2 ways to look at that, right? On the one hand, OCGI has many more features than the Java module system. So OCGI out of the box already supports the hot deployment, hot loading of modules, for example. It has all the lifecycle callbacks for bundles and for services, etc. So if your application uses that, if you have these dynamic lifecycle hooks that you use, then I would definitely recommend to keep on using OCGI.
Yeah, but sorry for interrupting you, but as we saw here in the speech, this lawyer system you presented here looks like a clear replacement of runtime modularity of SGI. Am I right, or am I missing something?
No, I mean, I showed you that you can do more or less the same using module layers. but the API around it is just much less rich than in OSGI. So if you really do make a lot of use of the dynamic lifecycle callbacks in OSGI, then I think moving to just plain Java modules will limit you. But I also had a second aspect to my answer, and that's more around tooling. I build a lot of OSGI applications. I'm really not that satisfied with the whole development and the tooling stack around OSGI bundles and development. There's BND, there's BND tools, which is really nice, but again, not perfect. With Java modules now being part of the language, part of the actual platform, we already see that the IDE vendors and the tool vendors, etc., are already moving much quicker on that than they ever did on OSGI. So to me, that is really an advantage of Java modules. The tool support and just the ecosystem support of it, because it's now officially part of the platform and it's not something that's just built on top by somebody else like OSGI. So for me, and this is part what I see happening now and part also still wishful thinking, of course, because we're not there yet. But for me, I see the tool support being much, much better for Java modules in the near future. So that's also a consideration that will be important for me.
I see. Thank you.
So if you have any more questions, I'll be at the discussion zone after this. And again, if you're interested in a free month of Pearl site, come on up here, I'll give you a card. And thanks again for your time and your attention.
Thank you, Sada.